In 1988, General Dynamics was awarded a contract by the Air Force to design and build a variable stability in-flight simulator test aircraft, to be known as Vista. Because of the amount of redesign required and the fact that there would be only one aircraft built, a decision was made to utilize computerized mock-up techniques instead of the traditional metal mock-up. This computer mock-up technique, or COMOC as it is commonly called, is only one of the advantages that were realized by using a three-dimensional design system. Throughout the rest of this program, you will see how this unique aircraft was designed and manufactured with the aid of advanced computer processes. Flight simulators have been used as an effective means of training pilots for many years. Most flight simulators are ground-based, but modern technology is greatly improving the quality of ground simulation to give it a more realistic feel. The ground simulators of today utilize state-of-the-art computer-generated visuals that surround the pilot to depict a scene as the pilot would see it. The graphics are generated to represent actual locations and are presented to the pilot from takeoff to landing. The first flying simulator, the NT-33A, is the predecessor to the Vista aircraft and has been used by the U.S. Air Force for the last 30 years. Information derived from the NT-33A has been useful in the development of many aircraft, including that of the F-16 itself. Vista is the newest concept in the development and use of in-flight simulation. Vista will be capable of simulating the dynamic and control system responses of future flight vehicles, including high-performance fighter aircraft. The principal theory behind this aircraft is that flight characteristics are varied by changing the software and not the hardware. The Vista airframe is a production F-16, modified to meet program specifications. Construction of models began with master dimensions database surfaces used to define the airframe envelope. From this database, primary and secondary structural parts were modeled and stored in a library from which zone models were created. The zone models depict all parts within a given area, such as the ammo drum bay or the conformal dorsal. These models define volumetric constraints and provide an interface for the design groups. Initially, many of the Vista-specific designs defined an envelope or volume reserved by the engineer. As the designs evolved, systems zone models were created and overlaid onto structural zone models to represent the current configuration. Coordination and communication derived from the zone models serve to define the configuration throughout the aircraft. The various disciplines working on Vista were co-located to facilitate coordination. Volumetric interferences detected through the use of COMOC were made known to the designers involved so that conflicts were discovered early on in the design phase, thus minimizing redesigns and schedule impact. In the concurrent engineering room, managers and engineers from several groups meet to simultaneously view the current configurations represented by the various zone models. Discussions include group coordination, status, and schedule. After review of design requirements and geometric analysis, an appropriate location for each installation was determined by the engineer. The forward equipment bay was selected for the heart of the variable stability field system. The installation is composed of the Titan Field System computer with 2 power supplies and the Logic Engage and Interface chassis with a single power supply. The system has the ability to vary the force field and motion characteristics of the evaluation pilot's side stick, center stick, rudder pedals, and throttle. Accessibility and a close proximity to the field system manifold is vital to this installation. Modifications in the crew station situate the evaluation pilot in the forward seat. The field system manifold is installed beneath the added center stick. The manifold is an electro-hydraulic unit which generates a signal from the pilot's input at the center stick. The signal is fed into the field system computer A proportional signal is generated by the throttle position and sent to the VSS computer. The raw data is then modified, and an output command is sent to a servo actuator, which positions the safety pilot's throttle to match that of the evaluation pilot's. This process eliminates transients during recovery from simulation mode. The right-hand console was selected for the disk drive cartridge, allowing quick access prior to or possibly during each flight. This component provides the flight characteristics of the simulated aircraft. The aft equipment bay is used for the installation of VSS, instrumentation, and production equipment because of the easy access it provides. The Raymond Disk Electronics Unit installation is located to be near the disk drive cartridge in the crew station. Space in the center of the bay has been provided for a provisional Kaiser reconfigurable display processor, which controls a variety of cockpit displays. Volumetric and weight considerations led to the installation of the Hawk VSS computers number 2 and 3 in the ammo drum bay. The Hawk computers receive inputs from the Titan Field System computer and the Raymond Disk Electronics Unit. The data is processed and transmitted to the digital flight controls, providing feedback to the pilot and commands to the control surfaces. The ammo bay cover was redesigned to allow access for troubleshooting and inspection. Pneumatic cylinders, actuated by an external source, lift the Hawk computers from the ammo bay. Environmental control system ducts provide cooling throughout this bay and the adjacent zones. Instrumentation units were installed in the right-hand strake and gun breech areas. Interface requirements determine the location for the sensor signal conditioning chassis in Dorsal Bay 2. The unit converts raw sensor data for use by the Hawk VSS computers. Removal of the one-piece cover allows for easy access. The AR-700 data recorder is used to store both the VSS and basic F-16 flight data. Some of the data recorded includes FM data, time code, and a voice track. The data recorder and video recorder require access prior to each instrumented flight. Because of this, the cover was redesigned with a hinge on one side. The in-flight refueling receptacle has sealed cavities on both sides available for equipment installation. The left-hand side is occupied by 3 data bus interface units used by instrumentation. Dorsal Bay 5 has a one-piece cover providing access to the number 1 Hawk VSS computer and the expansion chassis. Both units are installed on a common shock-mounted support. The F-16 has 2 separate hydraulic systems which provide adequate flow, filtration, and operational safety. The core Vista hydraulic system was modified to accommodate the fully developed 6 degree of freedom configuration. Changes include the addition of 2 100 cubic inch pneumatic reservoirs to the existing flight control accumulators, increasing the system line size to allow higher flow rates, and installation of 2 increased capacity pumps. The 51 gallon per minute pumps replace the 2 standard 42.5 gallon per minute pumps and are driven by the main engine through the accessory drive gearbox. Additional tubes were routed to the field system manifold for operation of the center stick. Working in a 3-dimensional environment gives the engineer a much more accurate picture to determine how a part should be designed. To illustrate this, let's describe how an actual design was created using a 3D system. The design process typically starts out with a definition of the task at hand. In this case, the task is to install the Raymond Disk Electronics Unit and a coaxial switch. First, it is necessary to create solid models to represent the electronics unit and the switch on the computer. The equipment is installed in the aft equipment bay, so the structure describing the aft equipment bay is extracted from one of the zone models. In order to attach the equipment to the existing structure, a combination of extrusions and sheet metal parts are created. In most cases, solids representing the parts are created by projecting a closed curve a specific distance and then subtracting other solids from it to create the desired shape. This type of operation is similar in nature to the machining process which makes actual parts. Once the basic design is constructed, standard parts obtained from a library are added to make the design complete. During the design process, it is important for the engineer to submit preliminary design configurations to the zone model coordinator, so any interference problems can be corrected as soon as possible. A final model is submitted when the design is complete. When the design is finished, the engineer can begin to create the dimension drawings to be used in the shop. Formats are placed on the Draw Space section of the screen, and auxiliary views are created which are actually just different perspectives of the 3D workspace. Filters are used so that only the desired part or combination of parts are seen in each view. After the views are created, dimensions and text can be added to complete the drawing. Finally, a print of the drawing rolls off an electrostatic plotter. Three-dimensional solid models provide a variety of analysis capabilities. Mass properties such as weight, center of gravity, and moment of inertia are determined for each component. Section properties of an area and moment of inertia are computed for use by structural analysis. Geometric analysis verifies clearance or interference of components. Kinematic studies simulate dynamic motion and assure proper orientation and function of components. Human factors and pilot vehicle interface studies can be used to incorporate reliability, maintainability, and supportability before a design is released. A unique aspect of 3D design is the ability to generate flat patterns from curved surfaces. One example of this ability can be seen in the design of the modified ammo drum bay cover that provides clearance for the Hawk computers to be raised and lowered. By creating a relationship between the edge of the cover and its surface, a flat pattern can be developed with the new edge line projected on it. This can then be used to make a template or for numerical control programming. Here, we see a laser cutter making a hole in the new cover. The 3D geometry can also be used for conventional machining programming, as we see in these animated replays of NC programs. The first sequence shows the cutter as it glides around the edge of the bracket from our design example. And this sequence shows more complex 5-axis machining capabilities. Almost 90% of the hydraulic lines in the aircraft were either modified or of a new design. This resulted in the need to manufacture over 400 new hydraulic tubes. Tubes were modeled as solids defined by a center line which retains attribute information such as diameter, wall thickness, and material. A tube is designed so that it connects the appropriate hydraulic equipment with adequate clearance to existing equipment and structure. Computer programs have been developed which extract tube bend data from the computer model. This data is used to verify that the tube is producible, drive the automated tube bending machine, generate visual aids, and provide a reference for inspection. The Vista aircraft will support Air Force aeronautical research and development over the next 30 years. Its existence will aid in the understanding of flight dynamics and will have a direct bearing on the design of future aircraft. Incorporating techniques such as computer mock-up and three-dimensional design are just a few of the ways General Dynamics is using state-of-the-art technology to achieve the best in aerospace design.